Hello, I'm Anna and I'd like to present my project of this semester, which is design of a two-stage op-amp. So, operational amplifiers are widely used in electronics for amplifying signals, and in this project I focused on designing a two-stage op-amp with high gain, high bandwidth, and stability. So, two-stage op-amp consists of two stages. The first stage is differential input to single-ended output for initial amplification, and the second stage is just a common source amplifier, which also includes Miller capacitance for feedback stability. And in this slide, the specifications can be seen, and in the end of the video, I will show that they are met. So the first and probably the most important part is figuring out the biasing of the circuit, because depending on how much current goes into each stage, the behavior of the op-amp will be different. Now, for example, it determines the GM, which then determines how much the signal is amplified. So on the left, the correct way of biasing is shown, and on the right, the incorrect one is shown. So the method on the left is better because it's a current mirror, so we can just easily choose the reference current and then adjust the aspect ratios of M5 and M7, and depending on their aspect ratios relative to M bias, we can easily control how much current goes into both stages. So then we can notice the trade-off between the phase margin, gain, and bandwidth. So without making significant adjustments, it's quite difficult to keep all these three parameters high. So one of them will be sacrificed. But it's actually possible to keep gain and bandwidth high and while increasing phase margin, and this is achieved by making the transistors much wider. So by increasing GM6, which shifts the output pole to much higher frequencies and increases the phase margin. But also we need to compensate for the undegraded gain by increasing GM1. And finally, after making these adjustments, we get the three main parameters satisfied: the gain bandwidth, the phase margin, and DC gain. However, as we can notice, the transistors become very wide, and it makes sense to divide them into multi-fingers. For example, as we can see, the M1 width was 60 micrometers initially, but I divided it into multiple fingers of 5 micrometers. And after that, we can check the power, which is 2.5 millivolts, and which is very high. But later I will show how we can decrease the power. Then we can also check the slew rate, and it meets the specification. And we can also check the CMMR, but it wasn't meeting the specification. However, we can improve it by increasing RSS, which is M5 in this case. However, the gain suffers a little bit. And finally, I show an alternative method of increasing phase margin without making that transistors very wide, which is adding an extra resistor in series with C. This resistor can be used to eliminate the RHP0 or even shift it farther to the left to cancel pole 2. So here is the difference after adding RZ. We can see that the phase margin instantly increased from 31 to 64, which is a great difference, simply by adding an extra resistor. And finally, we can see that power in this method is much lower. It's only 0.45 millivolts, which also makes the figure of merit much better. And finally, here is a summary of both methods. In the first method, the gain is slightly lower than it should be. However, the bandwidth is much higher, so it can be traded for gain quite easily. However, on the left, the power consumption is much worse. And in the second method, all the requirements are met. Thank you.